I said this theory states that simply that valence, it's valence shell electron pair repulsion theory. You don't even it's called valence shell electron pair repulsion theory. What it basically means is that bonds, they repel each other. We already learned that previously. Like if I draw this sp3 hybridized orbital, like this carbon atom that's making 4 bonds, uh, the bonds, or maybe I draw a simpler version. So the idea is that bonds in a molecule, they just repel each other. So if you have a carbon atom that's making 4 bonds, then the arrangement of that carbon atom of all the bonds in the three-dimensional shape, in three dimensions, it's going to be sp. One second. I mean, forget sp. It's going to be tetrahedral. That means that all the bonds are repelling each other. So one bond repels the other bond, and they all repel each other. So they all remain as far away from each other as possible. So it's like a pyramid, a three-sided pyramid with one bond on top of it. And that's a tetrahedral shape. So that's the idea of valence shell electron pair repulsion theory. Now, in your outer shell, you don't only have bonds, you also have lone pairs. So what happens is that the lone pairs also repel the bonds. So if I have an SO2 molecule, and I've got another SO2 molecule. So what will happen is that the bonds or the electrons in this bond over here and the electrons in this bond, both of them are going to repel each other. And they're going to stay as far away from each other as possible. But sulfur has lone pairs, which means that there's another bunch of electrons in the outer shell that are not involved in bonding. A lone pair is the outer shell electrons that are not involved in any sort of bond, which means that they are completely full orbitals. So sulfur has 6 electrons over here. Sulfur at the moment is making 4 of its electrons are involved in bonding, 2 over here, 2 over here, and there's the other 2 electrons out of the 6, they're not doing anything. Okay, over. So the thing is, that bonds, which is valence shell electron pairs, bonds, or bond pairs, and lone pairs, they all repel each other. And you have all types of bonds in the outer shell. All these electrons are repelling each other. So you have all sorts of bonds. You have in the outer shell, you have around an atom, you have lone pairs. That's the first one. And you have bond pairs. So you have a single bond. Okay, let's start with triple bonds. You have triple bonds. And you have double bonds. And you have single bonds. Now the lone pairs over here, they have the greatest. I said the lone pairs over here, they have the greatest repulsion. They exert the greatest repulsion. Their repulsion is stronger than any of the bonds. The bonds don't really repel that much. Lone pairs have higher charge density and they repel the other electrons more strongly. And I'm going to explain why just in a little bit. So they have higher charge density and they would have the strongest repulsion. Now the basic idea is the bonds are all, and the lone pairs, etc., they're all repelling each other. So they're going to be as far away from each other as possible in the three-dimensional shape. So I'm going to start with the first one. So option number 1 is, or the first case is, that if a molecule has 2 bond pairs, just 2, and no lone pairs, that's the first one. Now, if it has 2 bond pairs, then the 2 bonds, and the simplest molecule that I can think of is it's BeCl2. So if it has just 2 bonds, then both bonds would try to be as far away from each other as possible. So if you have a chlorine over here on this side, or electrons over here in the bond, this is a sigma bond, the other sigma bond would be on the complete opposite side because they're going to repel each other. So one is on the right side, the other one would be on the left side, and the angle that they're going to make with each other, that's going to be 180 degrees. And the shape of the molecule is going to be linear. It's going to be straight. So that is the shape of the molecule. Is this idea clear?
Yes.
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 And also remember that when you talk about bond pairs, and the way you count bond pairs, so you've got, let's say, carbon dioxide. This is also two bond pairs. What you should learn is to think of triple bonds or double bonds or single bonds as one thing, because the electrons are together. So that's, I mean, think of this as one pair of bond, although they're actually two pairs, but think of this as one entity. This is the other entity. So the bonds over here are going to repel the bonds over here. So think of this as two bond pairs. So this one would also be 180 degrees and it's going to be linear. If you have another one, let's say an HCN molecule, that's going to be exactly the same. So that's going to be exactly the same. It's a bunch of, it's two pairs of bonds. They're bonds over here and they're bonds over here. So they're basically two pairs, even though this is a triple bond, but think of this as one thing. And the two things would be as far away from each other as possible, which is why the angle would be 180 degrees. Is that clear?
Yes.
Yes.
Okay, so don't think of this as four bonds. Think of this as two pairs. This should be treated as one thing. Now the second one. Now, how do I know it doesn't have any lone pairs? The way I figure out that it doesn't have any lone pairs is, and why there are only two pairs of bonds over here is that if you look at beryllium, that's in group 2. So that means one electron being shared over here, one electron being shared over here. So the two electrons are used up. So there's nothing left in the outer shell. If you think of carbon has 4 electrons, 2 electrons being shared over here, 2 electrons being shared over here. So that's it. There's nothing left. Same applies to this carbon atom as well. So think of the total number of electrons that the atom has in its outer shell. How do you know how many electrons it's got? You can just look at its group number. And by just looking at the group number, you can figure out that if 4 electrons are being used up in 3 over here, 1 over here, so all 4 electrons are busy and there's nothing left. Now I'm going to talk about the second one. And the second one has different variants as well. So the second one is if I have 3 bond pairs. So if I have a group of 3 or 3 pairs of bonds, whether it's triple bond or double bonds or single bonds, the shape is going to be like a fan. It's going to be planar. It would be 2-dimensional, and it's going to be like a fan. So that's one. That's the other one. That's the third one. So this one is going to be a completely planar molecule. I've got a Cl here. I've got a Cl here, and I've got one Cl at the top. And the angle that the fan is going to make, it's going to be 120 degrees. You don't call it fan shape, you call it trigonal planar. So when you use the word planar, that means it's a completely flat 2-dimensional molecule. It appears exactly the way it's shown on this screen. There's no bond coming towards you or going into the page. So it's a completely flat fan-like structure. And there would be other examples as well. And how do I know that aluminium doesn't have any lone pairs? Because aluminium is in group 3. So if it's in group 3, that means one electron shared here, one electron shared here. So there's nothing left. Sulfur trioxide is also, it's also trigonal planar. So it's got a bunch of bonds. 3 of them. So there are 3 pairs of bonds or 3 pairs of double bonds. And they all repel each other. It doesn't have any lone pairs. Sulfur has 6 electrons, 2 shared here, 2 shared here, 2 shared here. There's nothing that is left. So that's about it. So moving to the third one. So the third one, sorry, there's another version of this. So this is the second version. And in this case, you have two lone pairs. Not sorry, two lone pairs, two bond pairs and one lone pair. Again, wrong, just a second. Two bond pairs plus one lone pair. Now, in this case, if you have two bond pairs plus one lone pair, what will happen is that an example for that molecule is we can have sulfur dioxide. Now, the shape is going to be exactly the same because it's still three pairs of bonds. Like there's two electrons in bonds and there's one lone pair. So it's still three pairs. So the shape is going to be exactly the same. It's going to be fan shaped. There's going to be an oxygen. And there's going to be another oxygen over here. And sulfur is, in this case, going to have one lone pair because 6 electrons, that means group 6, it's got 6 electrons, 2 shared here, 2 shared here. So there are 2 left. So that means there are 2 electrons that are left, and those 2 electrons are going to be over here. So the shape would be exactly the same. These electrons, they would all repel each other. So the shape would be exactly the same, except for the fact, think of this as a fan with one blade missing because there's no atom attached on that side. I mean, you've got a lone pair of electrons, but there's no atom that is attached on that side. So the shape exactly remains the same. But since there's nothing on this side, so that side, think of it as one blade missing from the fan, which was over here. And the angles pretty much remain the same, except that lone pairs exert greater repulsion, which is why the lone pairs are going to push the other bonds slightly closer to each other. So the angle, instead of like in the fan, the angle was 120, but now the angle would be around 117 to 120 degrees. It would shrink a little. And you can't call it fan shaped. You can't call it trigonal planar because if you look at a fan with one side missing, then that's not fan shaped. It's going to be called bent or non-linear. That is what the shape is going to be. Is this clear?
Yes.
Yes.
Yes, sir.
So now coming to the question, I told you that lone pairs exert greater repulsion compared to these bonds. So why is that? The reason why this is true is that the bonded electrons, especially the bonded electrons, they get attracted by some other atom. So the double bond electrons over here and the double bond electrons over here would be closer to oxygen. So they would be further away. If something is really far away, then there's going to be lesser repulsion. Lone pairs over here are right next to the atom. They're like really close to the atom. So something that is close by, that's going to exert more repulsion. So the only reason why bonded electrons, they exert lesser repulsion is because the bonded electrons, they get pulled by some other atom. And they're like further away from sulfur. Like sulfur's 2 electrons over here would be slightly further off. Sulfur's 2 electrons over here would be slightly further away. So which is why the lone pair would be kind of more dominant around sulfur because the lone pair would be right next to it. So it's going to exert more repulsion. So something that is far away, like if there's a piece of magnet that's really far away, it's going to have lesser repulsion. But if there's a piece of magnet that's like really close to it, then there's going to be a stronger force. The same applies to electrostatic force. If the electrons are like really close by, they're going to exert a much bigger repulsion. So this is what we had discussed. I told you that lone pairs have higher charge density, which is why they exert a much stronger repulsion. So whenever you have lone pairs, what happens is that the other bonds, they kind of become closer to each other because of the repulsion, greater repulsion exerted by these pair of electrons. Is this also clear?
Yes.
Yes, sir.
Yeah.
So I've got this one. This is bent in nonlinear, and so anytime you have one lone pair and two bonds. So remember, these two shapes are exactly the same, except that there's nothing attached on top. Like if there's nothing attached on top, then there's obviously nothing there, except for the electrons. So you don't count it in this shape. So it's no longer fan shape, it's just a V-shaped. You can call it bent nonlinear, or you can also call it V-shaped. So moving to the third one. Now the third one, that's a quick question is. So moving to the third one. The third one is if you have four pair of bonds, and starting with the 4A. 4A is when you have four bond pairs. So when you have four bond pairs, what happens is that it's going to be tetrahedral. So the prime example is CH4. So that one is CH4. And just hold on a second. Can you guys still hear me?
Yes, sir. We can.
Yes, sir.
Just a second. Let's go back. One second. So I've got CH4 that's going to be tetrahedral. We did that previously as well. So that one is tetrahedral, and the angles are 109.5 degrees, and all of them are exactly the same. And the other molecules, whenever you have four bonds, and the bonds could be any type of, you can have dative bonds as well. Like if you have NH3 which is forming a dative bond with now NH3 has a lone pair, and that lone pair gets attracted to an H plus one ion. So that is also going to be tetrahedral because basically at the end of the day, it's 4 pair of bonds, and those bonds would repel each other. And so the angle over here would also be 109.5 degrees, and it's going to be tetrahedral. Some more examples. If I have an SO4 molecule, it's going to be the SO4 molecule or ion SO4 minus 2 would be something like this. It's going to be having 2 O minus 1 ions, and there's going to be a double bond with an oxygen. 1, 2, 3, 4, and there's going to be another double bond with another oxygen. So that is also going to be SO4 minus 2 would also be tetrahedral because basically at the end of the day, it has 4 pairs of bonds. And then you'll have variations. First one is for part B, which is that in 4 part B, you will have 3 pairs of bonds and 1 lone pair. So this one, if you have 3 pairs of bonds, the shape would be exactly the same. It's still basically 4 pairs. So the shape would be exactly the same, except that there's a lone pair on one side. So NH3 is the main example for this. In NH3, the shape is still derived from a tetrahedral shape. Except there's nothing attached on the fourth side. You've got a bunch of electrons, and N has lone pairs. N is in group 5. So at the moment is making 3 bonds. So that means there would be 2 electrons that are not doing anything. So you still have electrons on the fourth side, except there's no atom attached on the fourth side. So the fourth side is basically missing. The electrons are there, but there's nothing attached on that side. And the lone pairs, they exert a greater repulsion, which is why the other bonds would be kind of closer to each other. So the angle would slightly shrink. It will become 107 degrees. And this would be referred to as a trigonal pyramidal shape. Okay, so remember to count the lone pairs, and the shape is exactly the same, but the angle is slightly smaller. One side is missing, so it's now basically just a pyramid. Here we can do 4 part C, which is another variation for the same. So in this one, you'll have 2 bond pairs and 2 lone pairs. Plus 2 lone pairs. So in this, what will happen is, and water molecule is the main example. So the main shape is exactly the same. So it's an oxygen. And I can start off with the tetrahedral shape. So it's the same exact tetrahedral shape. That's the starting point. Except in this case, you'll have an H, you'll have another H, but on 2 sides you'll have lone pairs because oxygen is in group 6. So that means that it's making 2 bonds. So out of 6 electrons, 2 are bonding. So that means 4 electrons are left. So the shape is exactly the same, except that this side wouldn't be counted in shape because there's nothing attached to it. So the angle was around 109.5, but because of the 2 lone pairs, the angle would shrink further and it would become 104.5. So remember these two. You can start off with the tetrahedral shape. That's the basic shape. If you have 1 lone pair, the angle slightly shrinks and becomes 107, and it becomes a pyramidal shape. And if you have 2 lone pairs, the angle shrinks further. And now it's no longer, you can't call it a pyramid even because even that side is missing. There's nothing there. So it's V-shaped. It's bent, it's V-shaped, or it's non-linear. V-shaped. You clear? Is this clear?
Yes.
Yes, sir.
Yeah.
It's a non-linear and bent. Was there a question?
Yes, hello, sir. Can you hear me?
Needs your voice is breaking.
Yeah, how about now?
Yes, it's fine.
Yeah, so isn't there another one called V-shaped or non-linear?
Yes, but that case the angle is different. I mean, V-shaped is anything that's like just this, just like a V.
Yeah.
That was derived from a fan shape. Like on one side you had a lone pair instead of any atom attached on that side, so it just became V-shaped. But that in that case the angle was 117 to 120. But now this one is derived from a tetrahedral shape, so this is also V-shaped, but the angle is a lot smaller because firstly there are two lone pairs now, so the angle is smaller.
Yeah,
Uh,
okay, thank you, sir.
now the next one is, so this was fourth, right? Four part A. Now the fifth one is if you have 5 pairs of bonds. So 5 bond pairs. Now in 5 bond pairs, what happens is that PCl5 is an example. So what happens in 5 bond pairs is you've got a P. Think of the P right in the center with a fan around it. So there's I'm talking about PCl5. So think of it this way. Think of it as the 3 Cls being as far away from each other as possible. So the angle is 120 degrees. It's like a fan. And then there are 2 more bonds, and those bonds are on top of the P, and one is going to be at the bottom of the P. So think of it as the fan hanging from the top, and there's something hanging from the fan at the bottom. Like the darker line, this one over here, it's not in the same plane. There's a fan. Think of it as it's as if the fan is hanging from the ceiling at the top, and there's something that's hanging at the bottom as well. So the 2 CLs would be over here. Now, in this case, there are going to be 2 angles. The fan will have an angle of 120 degrees. And the top bond and the bottom bond, they would have an angle of 90 degrees. And this is going to be called trigonal bipyramidal. So it's trigonal bipyramidal, which is this shape. There's a fan, one bond on top and one at the bottom. They're all repelling each other. So these 3 are as far away from each other as possible in a fan shaped, and one bond on top and one at the bottom. So that is what 5 bond pairs will give us, and they're going to be 2 angles. There are other versions of 5 bond pairs which we don't need to do because they've never actually ever asked any questions on that. We can jump to 6 pairs of bonds. So we can jump to 6 bond pairs. Now, in this case, you'll have, if you have 6 bonds and without any lone pairs, nothing. So the shape would be octahedral, which means that like if there's sulfur, then there's going to be 1 bond at the top. One of them is on the right side, one would be on the left side. One of the bonds would be at the bottom. So those are your 4 bonds, and then there's going to be 1 bond that would be coming out of the page and going into the page. So there's going to be 1 bond that would be behind it, and there's going to be 1 bond that would be. So this one would be coming towards you. So this is a molecule called SF6. So think of yourself as sulfur. There's 1 bond on top, 1 at the bottom, 1 on the right side, 1 on the left side, 1 in front of you, and 1 behind you. So 6 fluorines as far away from each other as possible. And the angle, the smallest angle, actually usually they talk about the smallest angle. So the smallest angle would be 90 degrees between the 2 fluorine atoms. Like this bond and this bond, the angle is 90 degrees, and this is going to be an octahedral octahedral shape. And we can do certain variations of the same shape. So there's a molecule of xenon fluoride, but I'll just do the variations very quickly so we can just start doing some past paper questions related to this. So one of the variations is, I mean, forget the atoms. Let's just use X and so let's just use random letters. This one is, let's say this is X, and it's bonded to 4 Ys. And there are also a bunch of lone pairs. So the lone pair, one lone pair would be behind it, and one lone pair would be in front of it. I mean, exactly the same shape. So because so this is not going to be a two-dimensional molecule. If you have 6 bond pairs, this one would be, let me label this, this is 4 bond pairs plus 2 lone pairs. So that is 6 part B. So that is that scenario. So now in 6 part B, you've got 4 atoms. So it's going to be completely flat. This is going to be square planar. So this is going to be square planar, and the angles are still 90 degrees, except that the Z dimension is missing now. Because behind that, there's no atom attached. In front of it, there's no atom attached. It's just one bond on the right, left, and one at the bottom. Okay, so is this clear? This thing, how do you figure out the shape of a molecule? You just have to figure out how many lone pairs it's got and how many bond pairs it's got. Is that clear?
Yes.
Yeah.
Yes.
And you've got to remember most of this, especially the simple ones like tetrahedral. And pretty much you can kind of, a lot of them you can just guess. Like if you know there are 3 pairs of bonds, then it's going to look like a fan. It's going to be trigonal planar. It's going to be 120 degrees. Or if it's got 1 lone pair and 2 pairs of bonds, and always to count a double bond as one thing. You can think of this as 1 pair of bonds, because these electrons, even though it's a double bond, but the electrons are together. So think of this as one entity. You've got tetrahedral, then you've got variations in tetrahedral, and then you have trigonal bipyramidal. These have several variations, but no need to go into that much detail. So I'll just quickly start with questions on this, and one second. Actually, this is molecular geometry and bond angles. So let's start at this point. So in this case, he's saying, I mean, the question states that ethane burns in oxygen and produces carbon dioxide and water. So you got ethane. If you don't know what ethane is, I'll just tell you it's carbon with single bonds. Now, one important point is that when you talk about the shape of a molecule, when you talk about a shape of a molecule, the shape is determined. So the shape is always, remember, determined by the central carbon atom in the middle. Like this carbon atom over here. This is the one that determines shape, or the one, it's never determined by the atoms on the outside, which is also applicable to any of these molecules. It doesn't matter how many lone pairs fluorine has. It's the middle carbon atom. You have to look at the arrangement of atoms or bonds, electrons, etc. around the middle carbon atom, not on the one that's on the outside. So always target the middle one. There are 2 middle ones over here. Now in this case, there are 2. So both carbon atoms have 4 bonds. So if you have 4 bonds, what is the shape? It's going to be, I mean, you can just have a look over there. If you have 4 bonds, the shape would be 4 bonds, the shape would be tetrahedral. So if I quickly draw these, both carbon atoms, the actual shape of the molecule would be something like this, that there's going to be carbon would be making 1 bond coming out of the page, and it would be bonded to another carbon atom that is also tetrahedral. So that would also have exactly the same shape. And there would be 3 H's, there would be 3 H's with this one, there would be 3 H's with this one. So think of 2 tetrahedral carbon atoms that are attached to each other, and the angle would be 109.5. Now, so it's going to be either C or D. And then he's talking about the combustion product. So when a hydrocarbon burns, you get carbon dioxide, which is carbon with oxygen, and you will also get water molecules. Now, the first thing is no one is going to tell you how many lone pairs it's got. You have to look for yourself if they've got any lone pairs. So carbon is in group 4, 2 electron share, 2 electron shares. So there's nothing left. No lone pairs, just 2 pairs of bonds. And 2 pairs of bonds would repel each other. The angle would be 180 degrees. So both of these are correct. And water, how many lone pairs oxygen's got? It's in group 6. So that means it's got 6 electrons. 2 are bonding. So that means 4 electrons are left. So basically you have 4 pairs of electrons, 2 lone pairs, 2 bond pairs. So the oxygen would be derived from a tetrahedral shape, except on 2 sides you will have H, and on the other 2 sides you'll have a pair of electrons. And the angle in this case would be 104.5, which would make it C. This is what we did for water just now. TK, is this clear?
Yes.
Yes.
Sir, when is the angle 90?
The angle is 90 in these, either in 5 bond pairs, it's 90, right? If you have 5 pairs of bonds, it's going to be fan shaped with 1 bond hanging on the top and 1 hanging at the bottom, right? So these bonds would be making angles of 90 degrees with the fan. And the other one was these scenarios, like if you have 6 pairs of bonds, the angle is 90 degrees. And if you have 4 pairs of bonds plus 2 lone pairs, the angle is also going to be
All right. 90.
So this one is a slightly difficult question. We'll keep that at the end. He's saying, which structure are 3 atoms bonded together in a straight line? So the first one is a polymer, polyethene. So if you do the first one, it's now if you, you can just Google polyethene for now if you don't know what that is. So it's a bunch of carbon atoms. They're all connected together and they're polymerized together. So if you look at each carbon atom, so each carbon atom is making 4 bonds. That means each of the carbon atom is going to be tetrahedral. So the actual shape of an ethene molecule would be a tetrahedral carbon atom attached to another tetrahedral carbon atom. So what is the angle in tetrahedral arrangement? Like when it has 4 bonds. Okay, anyone? What is the angle?
109.5.
Okay, so it's going to be 109.5 degrees. And always remember that the molecular formula that they gave you or the structural formulas that they gave you, that is not the actual shape. This only tells you how the atoms are connected together. Like if you look at an ethane molecule, then the 3-dimensional shape of an ethane molecule is like this. I mean that's an ethene molecule, but the 3-dimensional shape of this one is a perfect example. So it's like this. Remember, it's a 3-dimensional molecule. But when you draw it, structural formulas are like, if I just Google ethane and its structural formulas don't give you the shape of the molecule. They just tell you which atom. I'm still getting shape. So this one, a structural formula does not give you the shape of the molecule. They just tell you which hydrogen atom is attached to which carbon atom and so on. They just tell you the connections, like who's connected to which. So the shape of the molecule is always going to be different. So some people, what they do is they just look at this molecule and they think that this is 90. It's not 90. It's going to be a three-dimensional shape and the angles would be different. As anyways, you have C3H8, which is another alkane. So if it's in a straight line, the angle should be 180 degrees, which it's not. C3H8 would be similar. Like there would be hydrogens everywhere. I'm not drawing the hydrogen. So carbon is bonded to 4 atoms. So it's also going to be, this one is also going to be 109.5. Then you have SiCl4 that is also going to be making 4 bonds. So it's going to be tetrahedral. And 1 bond coming towards you, so SiCl4 that is also going to be tetrahedral. SF6 is where the bond angle is, it's not, where 3 atoms bonded together in a straight line. SF6, we drew SF6. So 3 atoms are bonded in a straight line. You've got fluorine, sulfur, and another fluorine. So they are arranged in a straight line. This fluorine, sulfur, and another fluorine, they're all arranged in a straight line. So this is the molecule where they are arranged in a straight line. Okay, is this clear?
Yes, sir.
Yes.
Yes.
So then you have another one. Which one has the smallest bond angle? So first one, BH3. So I know that H makes 1 bond, but the question is, so H makes 1 bond. But the question is, does B have lone pairs? It's in group 3. Can anyone tell me if it's got lone pairs in this molecule? It's in group 3. This one. It's
No.
not going to have lone pairs. So the shape is going to be fan-shaped, trigonal planar, and it's going to be 120 degrees. CH4, that is going to be tetrahedral, and the angle would be 109.5, right? C2H6 would be similar. Like if you just Google C2H6, then it's also 4 bonds. I'm not drawing the actual shape, but the 3-dimensional shape would be 4 bonds. That's going to be 109.5 as well, and it's going to be tetrahedral. NH3, will NH3 have lone pairs? N is in group 5. And how many lone pairs?
1 lone pair.
So it's going to have, because it's in group 5, but it's making only 3 bonds. That means 3 electrons are bonding. 2 electrons are still left. So this is, and there's going to be a pair of electrons on top. So this is derived from a tetrahedral shape, except there's nothing on the top. So it's going to be trigonal pyramidal, and the angle in this case would be 107. So this is the smallest, 107. So this one, are there any lone pairs on N here? It's in group 5.
Yeah, 1.
So
There'd be 1.
okay, what is the shape? 1 lone pair, 3 bonds. What's the shape of this one?
107.
Okay, that's 107. 4 bonds, that's going to be 109.5, right? And this one, what is the shape in this case? How many pairs of bonds?
3.
Okay, 3. So 3 is fan shaped. So it's going to be 120 degrees. So the answer would be X, Y, and Z. I mean, X is the smallest and Z being the biggest. So most of the questions are going to be really simple and straightforward. But the thing is, remember that, this one as well, most of the questions are going to be kind of straightforward. But the thing is that a lot of the properties of a molecule depends on the shape of the molecule. So that is going to count a lot. I mean, direct questions on this would be kind of small. And which molecule is drawn correctly according to the shape? Like the bonding is all correct. They're talking about this molecule. Let's do this last one. Is this carbon atom going to be linear?
No. Yeah.
Yes, it would.
It will, because it doesn't have any lone pairs. So there's a pair of bonds, 2 pairs of bonds. So this is fine. This is fine everywhere. So it's the same. What about this end? What would be the shape around this end? How many lone pairs would it have?
One lone pair. Should be 107.
So it's got, I mean, it's got one lone pair. How many bond pairs?
Oh, but then that would, oh, I see.
It's got one pair of bond and one pair of bonds. So it's basically got two bond pairs, right?
Yeah.
So that means it's basically three. Three is when you have this shape, right? Fan shape, right? So two bonds, and on one side there's a lone pair. So I mean that side won't even be counted in the shape. I mean it's basically
Yeah, but sir, didn't you say that if there's a double bond, you consider it as one?
so that's what I'm doing. It's one pair of bond over here and one over here. So it's two bond pairs, right? I mean it's
Yeah.
two pair of
So wouldn't
bonds,
that be 180 as well?
but there's a lone pair as well. So
Oh, I see.
So it's going to be this one. You've got two bond pairs plus one lone pair. So it's going to be derived from a trigonal planar shape. And it's going to be bent and it's going to be 117 to 120 degrees. Lone pairs and there are two pairs of bonds. It would be linear if there was no lone pair. Then it would be linear. Then you would have just these two and they would be as far away from each other as possible. But not in this case. The angle would be approximately 120 or 117 to 120. Is that clear?
Yes.
Okay, so we'll continue with this, but we'll move on to intermolecular forces now because shapes help us determine the intermolecular forces of a molecule. So we're going to do that. You just have to remember all of these shapes. That's important. Direct questions would be very small. Even the theory questions are kind of really straightforward. You just have to sketch the shape of a molecule exactly the same way. I mean, they might ask you to sketch the shape of AlCl3. You just do that. Or SO3, you just do that. You just draw this, that's it. Yeah, they might ask you to label the shape. So most of the questions would be very straightforward, but remember the shapes are indirectly important because properties and lots of physical and chemical properties would depend on the shape of a molecule. Okay. So let's continue tomorrow and we'll do intermolecular forces. And we will have a class tomorrow, okay?
Okay, sir.
Oh, okay, sir. Just one question.
Yeah.
Sir, are these classes for the May-June session or
They
is
are
this
for,
the class?
they are for the
Yeah.
May-June session.
Okay, and so the past papers will also be included in these?
Ah.
Okay. Okay,
We'll move more towards, make sure what you should do is now, tell me which topics to do, because we can switch towards more past papers. And
yeah,
we'll try and do chemical bonding and we
Sir,
will.
the first few chapters, they are the easy ones. Can you do the rest half, including organic chemistry, because those are the hard ones?
Yes,
yeah,
sir.
yeah.
So and and organic is more important. So after this, we'll switch to organic and we'll try and do their past papers a lot. Okay.
Okay, thank you.
So will you cover the chapters in between later or?
We can do them. It's I mean this one is big. Okay, this one is big. Apart from this one and up till excluding organic, most of the topics, the other ones are kind of smaller. They're smaller. You can do them very quickly.
No, like the enthalpy change one and
they're kind of they're not that big.
yeah.
So we can do them quickly. This topic
Okay.
and organic, they are slightly more time consuming. Okay. So after this, what we can do is we can switch to organic and focus on that a bit. Okay.
Sir, if we move in order, then won't that help us in organic?
No.
Okay.
I mean, a lot of these topics, they're not really that interlinked, especially organic. Okay.
Okay.
I mean, chemical, they're linked with chemical bonding, but not. I mean, you're doing organic. They won't give you enthalpy change questions with organic. Okay.
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 Okay, sir.
Okay, sir.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.